In this final video of the section about the module tilt angle, we will discuss mechanical tracking. We started this section by giving you the tools to calculate the irradiance for a variable tilt and azimuth angle. Then we applied this knowledge in order to find the optimal azimuth and tilt configuration to maximize the energy yield over a certain period of time. In this video, we are going to see the mechanical tracking system. By now, we have seen fixed and adjustable panel mounting configurations. Now we focus on the final method, which can be found in large PV plants and photovoltaic concentrator systems. The mechanical tracking systems can be divided into single-axis and dual-axis systems. For flat panel photovoltaic systems, trackers are used to minimize the angle of incidence between the incident sunlight and the PV panel. The primary benefit of a tracking system is therefore that the solar panel is continually tilted at an optimal angle, thereby maximizing the incident irradiance. Let's start with the single-axis tracker. As the name implies, this tracker only has one rotational axis, so 1 degree of freedom, indicated here by the red line. The tracking system consists of an electric motor controlled by a computer system that changes the tilt of the panel. The computer uses an algorithm that requires the coordinates of the location and the day and time to compute the position of the sun. This sort of system is called the daily or vertical tracking system because the axis of rotation is aligned vertically with respect to the ground. The electric motor can therefore tilt the panels during the day such that they track the sun as it moves from east to west. Another option is when the axis of rotation is horizontal with respect to the ground. When the axis is horizontal, the azimuth is kept constant and the module tilt angle is varied during the year rather than during the day. These systems are called the horizontal tracking systems, and they adjust their position according to the altitude of the sun during the year. So, during the winter solstice in the northern hemisphere, the panels will have the largest tilt angle. The tilt angle will gradually decrease until the summer solstice. Unlike the vertical tracking system, the electric load is much lower because the rotation cycle lasts an entire year. Note that in both cases it is very important to consider the shading in order to avoid unnecessary energy loss. Finally, we have dual-axis approach with 2 degrees of freedom. The first rotational axis is parallel to the ground and changes solely the tilt angle. The second axis is perpendicular to the ground and the other axis which allows for a change in azimuth of the panel. The dual-axis approach is often used for PV modules with the solar concentrators that require the direct component of sunlight. The dual-axis approach always makes sure that the direction normal to the panel is aimed at the direct component of light, as you can see in this animation. It is very similar to what we have seen with the parallelometer for measuring the direct normal irradiance. Here we have an example of a photovoltaic concentrator system that follows the sun during its daily movement in the sky. You can also see that, contrary to conventional photovoltaic systems, it uses so-called Fresnel lenses that concentrate sunlight to intensities up to and over 1000 suns. The sunlight is concentrated onto small and expensive, highly efficient multi-junction solar cells. This type of solar cells require high-capacity heat sinks to prevent thermal destruction and to manage temperature-related losses in electrical performance and lifetime expectancy. Therefore, a cooling system is generally implemented in concentrator PV systems. Nowadays, research and development is rapidly improving the competitiveness of concentrating PV in areas of high insolation. Let's compare the performance of a dual-axis tracking system with the performance of a PV system with a fixed tilt angle. We will now use the annual total amount of incident energy received by a surface to compare the performance of the systems. So, on the horizontal axis of this diagram, we have the incident energy for a system with a fixed tilt angle that is equal to the latitude of the location. On the vertical axis, we have the incident energy for a 2-axis tracking system, both expressed in kilowatt-hours per square meter. We consider, for example, the global irradiance incident on the module in Hamburg, in Germany, represented by the white circle. The annual amount of incident energy is about 400 kilowatt-hours per square meter, higher for the two-axis tracking system, going from 1100 to 1500 kilowatt-hours per square meter. The dual-axis tracking follows the sun to enhance the direct beam irradiance. So, if we plot the value of the direct component, which is the triangle in this case, we can see that 1000 out of 1500 kilowatt-hours per square meter are due to direct beam irradiance. The same comparison can be made for many other cities. As you can see, the energy incident on the module increases as the location gets closer to the equator, starting from Hamburg and going south towards Seattle, Rome, Hawaii, and Albuquerque. There, in New Mexico, the energy potential is almost 2.5 times higher compared to Hamburg, and the difference in annual incident energy between a two-axis tracking and a fixed system is about 900 kilowatt-hours per square meter. So it is clear that the amount of incident energy is much higher for a dual-axis tracking than for a fixed system. The difference is more pronounced in locations where you have fewer clouds, like in Colorado, in the United States, or New Mexico there, or Spain. One last thing I want to notice in this graph. If we do a linear regression of the circles which represent the global irradiance and the one for the triangles that represent the direct beam irradiance in the two-axis tracking systems, both increase with the different slopes. The fraction of energy received due to direct beam increases moving towards the equator. Indeed, it starts from a share of 65% in Hamburg and it reaches 76% in Albuquerque. So let's recap. In this video, we finished our exploration of the existing mounting systems. In particular, we discussed the single-axis tracking system, and depending on the orientation of the single rotational axis, the tracking system can be vertical for daily adjustments of the tilt angle, or horizontal, which adjusts the tilt angle gradually during the year. The alternative is a two-axis tracking, which is employed in photovoltaic concentrators.